It wasn't that I'd suddenly become converted to a belief in nuclear airplanes. It was rather this was the only avenue open for ORNL for continuing in reactor development. That the purpose was unattainable, if not foolish, was not so important. A high-temperature reactor could be useful for other purposes, even if it never propelled an airplane. He knew that to make the nuclear airplane work, they couldn't use water-cooled reactors. They couldn't use high-pressure reactors. They couldn't use complicated solid-fuel reactors. They had to have something that was so slick, that was so safe, that was so simple, that operated at low pressure, high temperatures, had all the features you wanted in it. They didn't even know what it was. I think someday this will be looked at as one of the great pivot points of history. That if this program, this nuclear airplane program, had not been established, the molten salt reactor would have never been invented. Because it is simply too radical, too different, too completely out of the ball field of everything else for it to be arrived at through an evolutionary development. It had to be forced into existence by requirements that were so difficult to achieve, and the nuclear airplane was that. Everybody who was pushing thorium said, we like thermal, this is the kind of reactor we want to build. And everybody who was pushing plutonium said, no, we want a fast reactor, that's the only way to do it. They by and large said, we're going to go the plutonium route. And one of the reasons why was they had developed a great deal of understanding about plutonium from the weapons program. They had made the stuff, they had worked with its chemistry, they'd made fuel out of it. They go, we get this. Thorium, we haven't really messed with thorium. You know, it would be like starting over. What the biggest problem is now is the technical development. We had a corpus of people in Oak Ridge who knew how to do this in the mid-1970s. They're literally dead and gone now. You know, I've met a handful of them, they're in their 80s. You know, they're not going to do this anymore. The first and hardest thing I think we need to do is to get this knowledge in the nuclear community. I've been in a nuclear engineering program for years now, and you don't get taught this stuff in nuclear engineering school. I got an email a few weeks ago. Once you know, I just graduated from Purdue with my PhD in nuclear engineering. I have never heard of this stuff before. And he goes, I'm going to tell you, it's even worse than that, because I'm totally a student of nuclear history, and I've never heard of this. How did I not hear this? 1,000 kilograms of U-233, which is roughly what we've got. You know, 90% of that will fission. We can make about $500–600 million in the electricity. Another $50 or $60 million on the fission of the uranium-235. Out of about 1,000 kilograms, about 15 kilograms of plutonium-238 will be left over. Now this is good stuff. NASA is desperate for this stuff. Plutonium-238 is different than plutonium-239, the stuff we use in bombs. This is the stuff NASA uses in its deep space batteries. Voyager, Galileo, Cassini, New Horizons, all of these deep space probes. We're completely out of the stuff. We stopped making it years ago. The Russians stopped making it years ago. We are out. If we don't get some, we're done exploring the outer solar system. This machine would actually make it in course of normal operation. In addition, it would make medical molybdenum-99. This is used in hundreds of thousands of radio imaging procedures every year. It's worth hundreds of millions of dollars. It would make 5 grams of that thorium-229 we could use in targeted alpha therapy. We don't even know how much that's worth. 20 kilograms of radiostrontium that we could use in radioisotope heating sources. This is the cheap stuff. It'll make xenon and neodymium. Almost everything that comes out of this reactor can be sold. You're looking at like $1 billion. There's such a thing as nuclear hacking. It's what this whole thing is about. Because we're not talking about nuclear technology the way it's done now. We're talking about a completely different approach to nuclear energy than everything we're doing now, and all kinds of improvements. I mean, where did our world of personal computers and all this stuff come from? Did it come from the IBM mainframes? No, it came from dudes having homebrew computer clubs in 1975. We'll look back in the future, and it's meetings and gatherings like this. We'll go, man, that was where it got started. It didn't get started at Westinghouse or Atomic Energy of Canada or GE. None of those guys are going to go build these machines because they're already locked into the solid uranium fuel stuff. They're locked into doing it the way we do it now. And you know what? The way we do it now, it's a really inefficient way to burn stuff because you can't let the fuel get very damaged before you have to take it out. You can't even come close to 100% burn. I mean, not even approaching it. I don't have a lot of faith that the current nuclear industry is going to take it on. And to be honest, what exactly do we want from them? I mean, all of their technology is based around technology that isn't what's going to go into this machine. All their money now is coming off fuel supply contracts. That's how GE and Westinghouse make money on nuclear power today. They don't build reactors, they sell fuel. Hey, guess what? I got a reactor. It's got no fuel fabrication to it. You've just upended their business model. okay, what about thorium? Well, what's so neat about thorium was in this book. So I started learning about it. The basic idea is thorium all by itself is not going to release nuclear energy. But if you hit the thorium with a neutron, and we'll explain where that neutron came in just a minute, the thorium will absorb the neutron, and it will turn from thorium-232 into thorium-233. Now, thorium-233 only has a half-life of like 20 minutes. So is it really radioactive? Oh yeah, it's smoking radioactive. Really, really hot stuff. You don't want to mess with your thorium-233. It's going to decay into protactinium-233, which has a half-life of about a month. Is this radioactive or less radioactive? Less radioactive, but still pretty darn hot stuff. You probably don't want to mess with this stuff either. And then it will decay over about a month to uranium-233, which has a half-life of about 160,000 years. Okay, much less radioactive. Uranium-233, if you hit it with a neutron, it will fission. It will split, like that chart I showed you earlier. But the cool thing is, in addition to releasing all that energy, it will release 2 or 3 additional neutrons. So you need one of those neutrons to go find another thorium, and you need another one of those neutrons to find another uranium-233 to continue the reaction. Let me tell you how this stuff was discovered. There was a guy named Glenn Seaborg who worked at Berkeley Labs in California in 1942. This was a guy who had discovered plutonium. And he had, coming off discovering plutonium, he thought, I wonder if we could hit thorium with a neutron and turn it into something. Again, remember, the neutron had been discovered like well, fission had been discovered like 3 years earlier, so they were still in the very beginnings. So he got this grad student, everybody's been a grad student knows what it's like when a professor says, all right, I want you to go into the nuclear lab and turn on the neutron bombardment system and expose this sample of radioactive material and find out what happens. And the grad student's like, it's a war right now, isn't it, sir, right? I could be on the front lines. Yes, you could. Okay, yes, sir, absolutely. Off I go. So the grad student went off and he did the experiment. And he came back to Seaborg and he said, yep, I've done it, sir. I have made something new. Thorium did absorb the neutron. It became uranium-233. Isn't that cool? Seaborg said, yes, absolutely. Okay, now let's take the next step. Poor little grad student. I want you to go back, and now I want you to hit it with a neutron and see if it will fission. Because I think it'll fission. I think it'll fission just like uranium-235. Okay, yes, sir. Goes off, does the experiment, comes back and says, yep, you were right. It did fission. You're correct. It's a new form of nuclear fuel. And Seaborg popped the really, really, really important question. He said, now I want you to go figure out how many neutrons came off when it fissioned. Because if that number is below 2, we really don't have a story here. If this number, you come back and it says it's like 1.5, then interesting fact goes in the back of the book. But if that number is above 2, then that is a big deal. Goes back, comes back. Sir, the number is 2.5. Seaborg looks at his grad student. This is December 1942, and he said, you've just made a $50 quadrillion discovery. Grad student's like, Seaborg was absolutely right. He had figured out that thorium could serve as an essentially unlimited nuclear fuel. And he knew how abundant thorium was in the crust of the earth, and he realized that through this process you could actually sustain the burning of thorium. Now, of course, you're fissioning uranium-233, but you're making a new one. So it's not really a catalyst in the true chemical sense that a catalyst is not consumed in a reaction, but you can almost think about it as a pseudo-catalyst. If you had some uranium-233, you could catalyze the burning of thorium indefinitely. Unlimited cosmic power from thorium. Well, maybe not quite that. It's pretty good. It's pretty darn good.